Our project topic is predicting floods as a consequence of deforestation. We all know how devastating floods have become in recent times, causing widespread loss of life and property. Torrential rainfall, coupled with human activities, are major players in causing floods. Moreover, the erratic climate these days makes floods very complex to model and predict. Moving on to the problem definition, by combining capabilities of GIS and machine learning, we aim to build flood inundation maps with accuracy being key. We also look to determine the deforestation extent and correlate it to flood occurrences.
These are the hardware and software requirements for the proposed system. The dataset used for flood inundation mapping are digital elevation maps, watershed boundaries, and stream flow lines. We use meteorological data and river stage height data for river stage estimation, and Landsat 8 and Landsat 5 satellite imagery for deforestation analysis.
Our proposed system is divided into three main modules: stage height estimation using LSTMs, flood inundation mapping using the hand model, and supervised land use classification for deforestation analysis. The data required for hand is the digital elevation map, which holds elevation of each point in the pixel in the raster. Terrain pre-processing is done on this raster for accurate calculation of flow direction and accumulation. Hand values are calculated for each point considering the vertical height of that point from the stream bed. Finally, these hand values are compared with the predicted stage height, and if the hand value is less than the stage height, it is considered as flooded.
LSTMs are used to model the entire precipitation runoff process and directly predict the stage height of the river based on meteorological conditions, removing any need for manual calibration. We chose the Cedar River Basin for evaluation of a model. Daily weather and maximum river stage height data over 40 years was collected from the three weather stations across the watershed. These observations were then aggregated to calculate each averaged weather conditions and stage heights. Once the inputs and the dependent variables have been aggregated, the dataset is windowed to make it usable for time series forecasting. A lead time of 3 days is used to forecast maximum daily stage heights in the next 4 days.
For deforestation analysis, the Landsat images were corrected and converted into composite bands to help identify different land characteristics. The training was done by taking spectral samples of a given feature identified by the composite bands and classifying them under specified classes like forest, water bodies, etc. Maximum likelihood supervised classification method was used to predict land features based on those specified classes.
And here we see the final results. This is the flood inundation map generated for the city of Cedar Rapids with the different colors depicting the areas inundated for different river stage heights. The color cyan shows the normal flow of the river, while purple shows the areas inundated when the river stage reaches 9 meters. The interface can be used to analyze the land use change in the area, with charts showing the changes in percentage of area of each land use class over time. These can be used to identify deforested areas which are affected by floods. A total of 10 model variations were tested using ANNs as the baseline. We chose the Nash Sutcliffe efficiency and mean absolute error to evaluate the stage estimation module. A Nash Sutcliffe efficiency of more than 0.5 is considered to be highly accurate. We see from the graphs that single output models with a horizon of up to 4 days perform exceptionally well with an error of less than 1 feet. As can be seen from the lower graph, the performance of the model starts degrading for lead times of more than 4 days.
Results of deforestation analysis. Figure 11 and 12 compare the change in the forested areas with time with respect to the number of flood events and the maximum annual flood inundation respectively. While figure 11 does not show any significant correlation between the forested areas and the number of flood events, figure 12 shows a marked correlation between the forested areas and the extent of flooding, with peaks in the maximum flood inundation levels corresponding to drops in the forested areas. Comparison with existing systems. Existing systems lack long-term flood prediction capabilities. Our proposed system will be capable of both short-term and long-term predictions without requiring human intervention and can be used in data-scarce regions. It will also give the extent of flooding in the region, unlike existing systems which cannot determine the extent of floods in a region.
To conclude, with lives at stake, maximizing accuracy and minimizing the flood effects by finding the geographical spread of these floods is key to our system. We also aim to alert the responsible authorities well in advance with time range of occurrence and regions to be affected.